Good afternoon, everyone. So, hope you guys are having a good show today. One of the things I noticed listening to the conversations today was the emphasis on AI and more so on cloud. When everybody thinks about AI, they think more of cloud. What we at Qualcomm do realize is that a lot of that AI is moving towards the edge, and this is more prominent or more visible when billions of devices are getting increasingly joining the internet and also processing more at the edge. When we say edge, sorry, how is this? There we go. So when we talk about edge, we are talking about not only the devices themselves, but also the edge cloud. Excuse me. So as billions of devices are sending more and more data, it's going to be a massive challenge on the cloud side to process all this data in a timely fashion. And what we realize is that not only processing this data is a challenge, but also ensuring that everything is done securely and maintaining the privacy is a challenge. And finally, attaining all this in real time. And that is the biggest hurdle that most of the devices have to do. The latencies are sometimes not acceptable to go to the cloud and come back. And here is where on-device processing, on-device sensing, on-device decision making, and maintaining security is going to change how things will evolve in the coming years. And for all this to happen, we need to have a set of technologies capable of doing all this. And this is where there are a whole bunch of challenges that arise. There are unique requirements that are required for edge devices because they operate in a very constrained environment. They have low memory or storage. They don't have too much processing power. Battery life is always an issue. And finally, thermal heat dissipation, and especially in small factor devices, is a challenge. And the requirements on the AI side are somewhat orthogonal because these are high compute, multiple concurrency models happen to run at the same time. They also need to happen in real time, and they need to be always on. So how do we marry or intersect these two different diverging requirements at the edge? Unless and until we solve that problem, we will not be able to truly have AI on the edge. Fortunately, improvements in technology at the edge are rapidly moving, or rapidly evolving, which is enabling us to not only sense devices, but also process, think, act, and reason. And at Qualcomm, we are able to not only converge all that, but we are also added connectivity, security, and edge services into the hardware solutions. So when we talk about reason, we are talking about how devices are able to learn, infer, and anticipate also. And finally, what's happening is that what's the missing thing here is we believe is 5G. 5G, we at Qualcomm will live, breathe 5G, and we believe that it's a unique connectivity fabric that is going to radically change the landscape for edge in the coming years. Just like how electricity is ubiquitous today, in a few years, we believe that 5G will be something that everyone expects to have. Just like today, you can't walk away anywhere without your Wi-Fi or LTE. We believe that 5G is going to be the same thing. Oh, I need to point there. Okay, sorry. 5G is unique in that it's been re-architected from a completely different perspective than the regular technologies. It's built for massive data, ultra reliable, low latency, ultra reliability and low latency. What it means is it is able to enable new use cases and applications that we have not thought about so far. And, and this will enable new experiences for the end user. For example, they really cater to three primary categories. First is the most common use case that we all think of, which is massive data, lower latency, and better experience. But the second category that really opens up for the massive IoT is all the stuff that they do, all the ultra reliability and ultra latency enables machinery, manufacturing, etc., without having challenges. And finally, 5G enables low power wide area networks by switching down to what you call as narrowband IoT and LTE-M that is available today, but it's derivative in the next generation. Being in robotics, sorry. So I'm from robotics in Qualcomm, and nowhere else there's this convergence of AI and 5G happening as we see all these kind of use cases where this takes off. I think this is where I'll hand it over to JB.
Thank you. All right, so we're going to have probably like 30 seconds to switch the presentation. But basically, I think I'm going to look at the problem from a software side now. I'm going to start with the last slide and try to explain basically what are we missing today in the software land in order to address all those applications. So we have like all these robots, those beautiful robots, and they need to live in the environment. And for this presentation, I'm going to try to convey like three different types of messages. The first one is going to be what's the state of the required software to address those problems. The second one is going to look a little bit at the IoT at the edge. Why do we need to have certain applications that live actually on the device or on the premises? And at the end, I want to open a little bit the perspective and to show you that when we talk about the robotic platform, a robotic operating system, the navigation technology is only one small piece of it. And then for this presentation, I'm also only going to focus on commercial robots in one segment of commercial robots that we call autonomous mobile robots, AMR. And they are robots that are like fully autonomous, where you do not require to change the environment to actually deploy them, that can work alongside people. So safety is not an issue. They can move around, and it's like people can, you don't need like dedicated, like trained people to be around the robot to operate them. And then they live in a complex and evolving environment and many different types of environments. And if you look at the projection of this industry in the next 5 to 10 years, this is a $100 billion revenue industry. And 80% of this industry is captured by AMR. So what we will anticipate is to address all these challenges. You will anticipate that there's a platform, there's a set of tools that allow like robotic builders to actually develop them, to deploy them, and to support them in the field. But if you look at the reality today, there is not a trusted foundational technology that allow people to do that. It will be, if you go back like maybe in the early 80s, before there was like this convergence between Microsoft and Intel that created like the Intel platform. Every time that you wanted to write an application, you had to rewrite all the primitives, and that wasn't scalable. Okay? So if we want to make another parallel, let's see if it works for me. Yep. If we want to build an airplane, that will be like the type of airplane we can build today with the type of technology we have for the robotic industry. And we actually see a lot of companies doing robotics today that you see in the news. They probably have like 10, 50, 100 robots, but they cannot scale. They cannot go to the 1,000 robots, to the 10,000 robots. The question is why? What is missing for them? Okay, so the first obvious reason is that building a complete robotic solution is really hard. And the reason it's hard is first, like all the robots seem to be different, right? if you take a robot that is cleaning the floor, it's very different from a robot that is doing delivery. And form follow the function, so you need to create a different type of body. You have some application-specific behavior, so the way that you're going to scan the item on the shelf only makes sense if you want to scan item in the shelf. And then you have like other set of differences that are really important, but that people usually underlook, is the sales channel, the customer support channel. But for all this technology, there is a common piece. There's a majority of the technology that is shared across this technology, that is shared across all this industry. And one of them that is really important is the navigation system. So it's like the way that you can deploy the robot and the robot can understand the environment, create a map of the environment, and then move in this environment. It can localize itself, it can avoid obstacles, and it can realize the task that it has to do. And if you are talking about floor care equipment, inventory equipment, or delivery equipment, the way that they can represent their environment is the same. So why are all those robotics companies recreating the wheel? Because if you look at what people do, every time they create a new application, they will recreate the navigation system. And the reason why they do that is that usually it seems like very deceptively easy to create a good prototype. You can go online, you download like some software package, and after like days or weeks, you have a solution that works 80% of the time. But to get it from 80% of the time to 100% of the time, this is where the real challenge is. This is what takes you years and years, like to find all the corner cases and to address all the data that you need to accumulate in the real environment in order to see how the system really operates. So autonomous navigation today is the bottleneck to this Cambrian explosion of robotics, to this explosion of robotics that is going to address this market in the next 5 and 7 years. So let me show you a few examples of the primitives, like these AI primitives that need to live on the robot itself. So when we are talking about AI on IoT at the edge, that means this needs to live on the robot, because without those technology on the robot, then the robot will not be able to do what it's supposed to do. And I've taken like four different primitives just to show you that, a lot of time when we talk about AI, we only focus on deep learning and the way that we can make inferences about the world. But when you are talking about robotics, it's a combination of things that are sometimes very low level, sometimes technology that have been there for probably 10 years, but that needs to be robustified, and sometimes even like deep learning technology. But this is a combination of the four of them. So on the top left, what you see is actually how the robot can understand its own displacement of the environment. So when you actually move as a human in the environment, you use like the information from your eyes to calculate your own displacement, turning left, turning right, moving forward. This is called the optic flow. So we have like similar solution working on the robot itself. Then if I show you another video, so that's actually an example with deep learning. This is where the robot learns the traversable area in the environment. So same thing, it needs to be done online. It cannot be done in the cloud and then and move back to the robot. That would take like too much latency. But that show you actually like the floor is obviously not green, but it's just like this algorithm that detects where the robot can go, and that will just like print or color the floor green where the robot can go. Another important example in robotics, this is called simultaneous localization and mapping. This is the way that the robot can build its own representation of the environment. So on the left, you can see the camera of the robot moving, and on the right, you can see like the map being built. I don't think you can see the position of the robot, but basically you will see that the robot localized, and at the same time as it localizes, it can construct a broader representation of this environment. And finally, this one is just to show you a little bit like the internal state of what the robots see in the world. So this is combining many different information from different sensors. So you have like LiDARs, you have 3D cameras, you have sonars, and then it needs to converge all this representation into something coherent so that it can navigate and avoid obstacles efficiently. And that's mostly sensing and acting independently at the edge. But there are other things that you can do as well at the end, or that you might want to do. Whoop, and it's over. Okay, so there was if we go back a little bit, can you go back maybe 3 more slides? Okay, this one. Yeah, so computing at the edge. When you have a machine that's operating in the environment, it's not only about navigating. You might want to do something with this data that you collect. So let's say that you have a robotic floor scrubber that is like moving in your environment. This robot has cameras. It can scan items on the shelf, and then you can detect if there is a missing element. You can detect if you are compliant with with what you are supposed to see in the shelf. And you might not want to push all this data to the cloud for data security reason, or just like the bandwidth that will be required will be just too big. So you might want to keep that in the premises. So that's an example of things that you want to do at the edge. All right, let's see. Okay, so the last part, and I will try to be fairly quick on this one, is just to show you that often people make the mistake of thinking that once you have nailed the navigation software stack, then you have the solution that you can scale. And once you're actually doing that, you realize that the navigation software stack, when you build a robotic operating system or a platform for robotics, is a very, very, very small portion of what you have to do. So first, if you think about the autonomy SDK, yes, you need a safety certifiable robot. So you need like safety embedded in the system. You need like the build environment, the tools, the connectivity. You need the activity framework, and everything needs to be documented. And you want to make sure that the people building on top of it can actually leverage from this technology. But more importantly, you need a set of tools and you need a set of apps that will allow you to deploy the machine efficiently. So if you need to send an engineer on site every time you do deployment, you are not going to be able to scale. If you need to deploy to 10,000 different environments, you are not going to send 10,000 engineers on site. So having those pieces that allow you to do the deployment and the maintenance of the robot are extremely important. Same thing with the development of the solution and manufacturing of the solution. So the autonomy piece, if you look at the broader picture, is going to be only a small piece of the overall equation. And I don't know if I still have 1 minute, maybe. I just wanted to show you actually a video of robots, because we have been talking about robots, but we haven't shown any. So it's just a quick summary of what we do and some of the robots that we deploy in the environment today. All right. So I don't know if anybody has a question. I don't even know if we have time for questions.
Maybe one or two questions.
Okay.
So you talked about all of this computing need to be at the edge, and then kind of, sorry, thank you. You talked about all this computing need to be at the edge, and then a little bit blurred the line between edge being on device and in the network, probably in a mech. What portion of the robotic operating system do you think can be moved off premises using 5G versus what needs to run locally on the hardware?
So I think it's going to be a gray area. So definitely, like the safety aspect needs to live on the robot itself. Is it AI? Somebody could argue that it's not like really AI. But I think like the very deep, like low-level primitive needs to live on the device itself, because even if you have low latency, you cannot take the risk of losing this connectivity. Then when you move towards something that is a little bit more creating a map of the environment, for example, or doing some detecting an obstacle but is not critical for safety, maybe that can be pushed to the premises, maybe not to the cloud, right? But still within the connection of the robot. And then all the reporting aspect, all the software update aspect, all the data connectivity can be pushed to the cloud. But there is like a kind of a blurry line between like those three things.